Bright glowing material erupted from Mount Etna's crater, shocking scientists on site. As instruments went off the charts, researchers struggled to identify what poured out, confirming Mount Etna erupted. Scientists lose it. The eruption began without warning. From Etna's southeast crater, a bright, almost electric glow poured upward, unlike any lava the team had ever seen. The molten material shimmered white-blue, reflecting through the thick, sulfurous ash cloud. Pyroclastic surges slammed down the flank at over 140 kilometers per hour, incinerating ground that had already been scorched. Field teams scrambled for position, boots sinking into still hot terrain, faces masked against the acrid air. Thermal cameras registered spikes beyond their limits. Drones wobbled against turbulent currents, barely relaying fragmented footage. Instruments beeped uncontrollably, warning of unstable heat zones and radiation levels inconsistent with normal eruptions. Geologists exchanged urgent words over crackling radios, eyes wide as charts and monitors began displaying anomalous readings.
Threatened magnet! Already! On top of the world!
Nothing in Etna's modern history resembled this. The ground shifted unpredictably, vents expanded, and fissures vented plumes in all directions. It was immediately clear this was no standard volcanic event. Ancient warning signs echoed in the team's minds. The last time Etna exhibited similar internal patterns, disaster had followed. And as cameras captured the first glow, the mountain's secrets started revealing themselves. Scientists and volcanologists navigated a battlefield of molten rock, ash, and collapsing earth. Thermal cameras tracked shifting hot zones while drones struggled to maintain position above the turbulent flows. Sampling kits and spectrometers were clutched tightly, every tool a lifeline in conditions that defied protocol. Fissures opened beneath their feet, venting scalding steam that rattled helmets and sent equipment skittering across the ground. Sensors beeped warnings of sudden thermal spikes and unexpected gas surges, carbon dioxide, sulfur dioxide, and trace radiation from unknown materials. Electronics failed without notice, forcing the team to improvise with handheld devices, phones, and portable analyzers. Sweat and ash coated faces, but retreat was impossible. Every step required careful balance, observation, and instinct. Radio chatter snapped as leaders coordinated real-time measurements, tracking the lava's unpredictable path and the shifting terrain. One misstep could mean being trapped by a surge or falling into a vent. The chaos was relentless, yet the team pressed forward, determined to collect data that could redefine understanding of Etna's inner workings. Every step could be the last, yet the team presses forward. Back at the mobile lab, the sample from Etna's glowing flow stunned scientists. X-ray diffraction returned no match in any known terrestrial mineral database. Under ultraviolet light, the fragment pulsed with intense fluorescence, glowing bright blue-white. Gamma sensors immediately spiked off-scale, readings that defied standard calibration. The material refused to melt, even under temperatures exceeding 1,600 degrees Celsius, far hotter than typical volcanic glass or basalt could withstand. Spectrometers, Geiger counters, and trace element analyzers all produced anomalies, rare lanthanides, unusual isotopic ratios, and chemical signatures normally reserved for deep mantle xenoliths. No instrument or known reference could explain the fragment's composition. Scientists debated whether the material originated from previously unmapped reservoirs deep beneath Etna or represented a novel reaction within the magma under extreme pressure. Emails and video calls flew between European laboratories, each result confirming the mystery. Every test pointed to one unsettling conclusion: Etna was drawing from processes and sources never observed in human recorded history. This was not just a volcanic anomaly, it was a window into the mountain's hidden inner workings. But this sample is only the first clue of deeper changes below. Geologists quickly drew parallels with Etna's prehistoric behavior. Records indicate that 7,200 years ago, the southeastern flank collapsed, triggering a massive tsunami across the central Mediterranean.
Anybody who was still alive and not been killed by a collapsing roof would have seen almost like a cloud coming down the volcano towards them. It would have been almost imperceptible. It was so far away how fast moving it was.
Internal reconstructions now reveal that Etna's magma chambers and vent alignments resemble conditions from that period. The southeast crater has swelled and shifted, echoing the ancient stress patterns that once destabilized the mountain. Thermal imaging, seismic data, and satellite radar all show a resurgence of similar inflation and flank bulging. The eruption's paroxysm, sudden violent bursts of molten material, mirrors events from millennia ago. Scientists warn that the glowing unknown material may be a symptom of these deep processes resurfacing. Villages along the slopes now face the unnerving possibility that history could repeat itself, with catastrophic consequences for Sicily and surrounding regions. Researchers monitor stress lines and microquake networks, tracking shifts that hint at potential collapse. Every measurement raises tension. Is Etna merely signaling a minor disruption, or is the mountain once again preparing for a large-scale failure? Ancient patterns emerge, suggesting the volcano's internal systems are reaching a tipping point. Once the sample reached the INGV lab in Katana, chaos ensued. X-ray diffraction, mass spectrometry, and Raman spectroscopy produced results that contradicted one another. Berlin's geochemistry team reported trace elements far beyond normal volcanic ranges. Paris analysts questioned lattice structures, suggesting either a new high-pressure phase or contamination. Video calls and encrypted emails flared between labs across Europe, with scientists cross-checking calibration, chain-of-custody protocols, and instrument integrity. The anomaly defied replication at first, sparking debates over methodology, but repeated tests confirmed the unknown composition. Even seasoned volcanologists admitted they had never seen data like this: gamma spikes, extreme UV fluorescence, and melting resistance far outside any known range. The implications were profound. If verified, the discovery could rewrite understanding of mantle processes and volcanic evolution. Every update was time-sensitive, triggering rapid peer consultations and emergency data uploads. Labs moved under unprecedented pressure, aware that Etna's next eruption might offer no warning, making the scientific window both urgent and perilous. Across Europe, teams worked around the clock, capturing, testing, and retesting every fragment, every measurement, every anomaly. Data streams collide, and every new reading deepens the mystery surrounding Etna. Meanwhile, spaceborne instruments and ground sensors painted a chilling picture. High-resolution satellite interferometry revealed the southeastern flank shifting faster than historical models predicted. Thermal imaging detected expanding hot zones tracing fractures beneath the surface. Ground sensors recorded hundreds of microquakes per hour, subtle tremors pulsing through unstable slopes. The southeast sector showed asymmetrical inflation, mirroring patterns from Etna's ancient collapse. Pressure readings, gas emissions, and surface bulges suggested magma migration into previously unmonitored conduits. Analysts warned that if acceleration continued, small shifts could cascade into massive structural failure. Models projected potential rock slides, proclastic flows, and even tsunamis in the Ionian Sea. Civil defense teams monitored every feed, aware that a chain reaction could unfold within hours. Each anomaly compounded the uncertainty. The mountain no longer behaved like a predictable stratovolcano. Every sensor reported a living system, dynamic and volatile, forcing scientists to reconsider response protocols. The data underscored a stark reality. Etna's unrest was not isolated. Its internal pressures now affected both local stability and regional hazards, demanding constant vigilance as the volcano edged closer to a potential disaster. The ground itself seems alive, pulsing beneath sensors in real time. Down in Soprana, Milo, and surrounding villages, life hung in delicate balance. Families debated evacuation. Some packed essentials, bringing children and elders to safer ground, while others stayed, unwilling to abandon homes built atop centuries of volcanic soil. Local farmers wrestled with leaving vineyards and olive groves behind, knowing the land's productivity came at the price of risk. Civil defense advisories shifted hourly, some warning of imminent danger, others advocating caution, creating confusion and tension. Radios buzzed with rumors, conflicting reports, and last-minute updates. Elder residents recalled historical eruptions, weighing ancestral knowledge against modern warnings. Children learned routes by rote, practicing drills while adults argued over timing. For many, Etna was both protector and threat, a source of fertile soil and life, yet capable of sudden destruction. Decisions carried weight beyond property. Livelihoods, memories, and community cohesion were at stake. Each choice reflected a negotiation between fear and attachment, uncertainty and trust, highlighting the human element in the shadow of a mountain increasingly out of control. While authorities debate, residents face choices that could change everything.
Italy's Mount Etna volcano has erupted, sending sparks of lava into the sky. Vision shows lava spitting high into the early morning sky and smoke rising from the volcano's crater. Mount Etna is the tallest and most active volcano in Europe.
Beneath the surface, Etna communicated in a language of vibration and sound. Infrasound detectors picked up low-frequency surges, acoustic signals resonating from kilometers below the southeastern flank. Each tremor traced pathways of shifting magma, some following channels that had been dormant for millennia. Sensors measured pressure fluctuations, thermal spikes, and ground deformation, revealing an internal system far more unstable than anticipated. Analysts noted that these pulses were unlike previous patterns. Small tremors now triggered rapid shifts across neighboring fractures. The mountain's heartbeat accelerated, a chaotic rhythm that suggested even minor triggers, rainfall, summit eruptions, or seismic tremors, could initiate a catastrophic collapse. Every new reading confirmed that Etna was no longer a predictable stratovolcano. Acoustic mapping indicated magma was moving in unexpected conduits, forcing scientists to revise hazard models in real time. Thermal anomalies along fractures mirrored seismic spikes, a feedback loop amplifying internal stress. With each measurement, the urgency grew. The mountain could strike without warning, and the window for preparation was narrowing. Every tremor, spike, and pulse reminds us of Etna's unpredictable force. Back in the labs, scientists wrestled with implications of the unknown material. Its ultraviolet fluorescence, gamma spikes, and resistance to extreme heat suggested processes reaching far below Etna's shallow magma chambers. Could this indicate previously unseen mantle activity, channels of molten rock untouched for millennia? The discovery challenged established volcanic models, traditional eruption patterns, flank stability estimates, and hazard forecasts no longer aligned with the data. Researchers debated whether new chemical compounds could alter eruption dynamics or trigger previously unrecorded explosive behavior. Simulations ran continuously, modeling potential pyroclastic flows, flank collapses, and even distant seismic ripple effects across eastern Sicily. Some theorized that if deep mantle processes were interacting with the surface, Etna's hazards might extend beyond local areas, influencing regional fault systems or coastal risk. Every new sample and spectral reading raised more questions than answers. The mountain's inner workings appeared to be in flux, a living laboratory for phenomena never before witnessed. As results poured in from multiple European labs, the magnitude of the unknown became clearer. Etna's eruption could redefine volcanic risk in ways never imagined. And if this eruption is a warning, what's lurking even deeper? Even hours after the eruption, Etna remained inscrutable. Field teams reported shifting fissures, thermal spikes, and unpredictable gas emissions, while drones captured footage that challenged prior hazard maps. Laboratories continued testing the glowing material, yet results remained inconclusive, producing more debates than answers. Satellite imagery and sensor networks showed continued flank creep and summit inflation, confirming the volcano had not returned to any normal rhythm. Scientists warned that even minor triggers could cascade into a sudden collapse or explosive surge, but precise predictions were impossible. Communities below the volcano watched tensely, following advisories that could change by the hour. Historical parallels hinted at danger. Etna's behavior was breaking the rules. The mountain had shifted, its inner workings revealing an unprecedented combination of heat, pressure, and chemical anomalies. Monitoring would continue around the clock, but the questions persisted. Had a new geological era begun? Was this eruption an isolated event, or a harbinger of far larger changes? With each passing hour, the mountain's next move could change everything again.